this on here, right? And it's called week 2 sample problems truss intro. So if you open the file, these dots are kind of annoying, but that's what you're gonna see. So this is before I had this video recording thing, so I wrote all the processes in one go, which you can read, which basically what I'm going to follow. So this is, you wouldn't call this a truss, but I mean, it's the first one that we did, the single triangle, that was actually called simple truss, right? And if you keep connecting two members, one joint, it's a simple truss. So you could call this a truss, and it's the simplest configuration of the truss, so it's the best to, it's the simplest format, so it's kind of good background for us to show you how to analyze the truss. And it's basically going to be the same process for something more complicated than this, but for the sake of demonstration, this is easy. So let's assume a triangle that's symmetrical, and it's made of 3 members and 3 joints, pin joints, right? And then you have 2 reactions, as we talked about last week. One is a pin joint, the other is a roller joint. And you could argue for pin joint we do have 3 reactions, or it has a capacity to have 3 reactions, but in a way this we know that's 0, because there's only, for sure, if this applied force at the tip was diagonal, right, it's gonna have a component that is horizontal, right? So it's gonna have a vertical component and a horizontal component. So that's gonna, if the applied force is diagonal, then the reaction at point R, it's going to have a horizontal reaction like that. But for this particular problem, we are just looking at this vertical applied force. So we have 0 amount of horizontal reaction here. Anyway, so we are basically going to learn how to determine whether each of these cores, RQ, QS, and RS, whether they're in tension or compression, and how much force there is in each of these cores, right? And as always, the force scale, who didn't take structure 1 with me? It's actually quite a bit. Okay, so remind me to, if you don't understand what I'm saying, then let me know, because we did this graphical method, so I'll try to make sure that you guys get it. But anyway, so we're gonna solve this graphically, meaning that we are not gonna do a lot of calculation, but we are gonna draw a diagram of how the force flows in this truss, and we are actually going to draw everything accurately to scale. We're gonna measure the vectors and then determine how much force there are in each of these members. So that's why we are drawing these forces. We are representing these forces with arrows, with vectors. But first rule is that it's absolutely necessary that they are drawn to scale. So for example, I'm showing this as 5,000 pound. I'm representing that with 50-inch long arrow. So therefore we do have this force scale. So 50 inches represents 5,000, no, that's wrong. 5,000 pound force, right? Therefore 1 inch represents 100 pound force. And because this is symmetrical, right, the reactions on these two ends gotta be equal and half of these, right? So on one side you have 2,500 pound force on both sides actually. So that's the reaction, and I'm drawing that at exactly 25 inches because this arrow should be always proportional and following this force scale, right? That makes sense? All right, cool. So now we are gonna go to the next step. So first step of this graphical solution for the truss analysis is by taking the outside of the truss and you kind of label these regions which is divided by these forces. So if you assume, so let's say very diagrammatically, right, this truss and these three forces can divide the world in three different domains. It's gonna sound weird, but this you don't have to draw. This is I'm trying to explain something. So let's imagine we are in 2D world, right? So let's imagine the entire world is circle, right? You have the inside of the truss and outside of the truss. So this is one area. I'm gonna use a different color. That's one area. But also these forces, if you imagine, forces has these lines of actions, right? So let's kind of assume that you're extending these forces infinitely. So now the world is divided into 1, 2, 3, 4 regions actually. Whoops, sorry. 1, 2, 3, 4 regions. And let me just, I'll share this script with you at one point. Just gonna color these 4 hatches. What? Oh, okay. So hatch is, whoops, sorry. So one region, two regions, 3 regions, and then what? Right, so you have these 4 separate regions, right? Is that clear, right? So I'll bring it back to here. Right, so now you can see, so basically we're labeling all these separate areas. I'm not going into, well, this is a really simple truss, so I'm not going to go inside the truss. So we're just looking at outside of the truss, which is divided into these 3 regions, right? So between this reaction on the point R and the applied force at point Q, that's one region, and we're going to label that as A. On this side, between this applied force and that reaction, I'm going to call this as B, right? And then between these 2 reactions, I'm going to label that as C. So that's all that's going on in that diagram. So hopefully that's clear, right? So there's A, B, and C between all of these forces. So that's the first step. So first you label the regions between the forces outside of the truss with alphabets. Next step, yes, there's also a region inside the truss. Just to distinguish the outside world and inside world, we are going to label the inside of the truss with numbers. So in this case, we only have 1, but we're going to get to more complex one later. For these, we're going to number all of these with like different numbers, but for now, we're using this really simple truss, so there's only 1 region. So that's the first step, is labeling outside and inside of the truss. So A, B, C, and 1. So far so good? Yeah. Then next step is, alright, so that's a wrong text. It's actually a force diagram. So we're gonna call this a form diagram because this accurately represents the form of the truss, right? Dimension and angles and all that. So this is what physically the truss looks like. We're now gonna start what's called a force diagram, which is only going to diagram the forces and has something to do with the geometry of the truss, but it's not going to look like the truss, but it's more like it's going to analyze the flow of the forces in this truss. So first step is by, okay, I'm drawing it in here, but I'm going to start new. First step is by, you basically want to sort of put aside all of the forces that you see to the side, right? So we know that there are one applied force going down, and we know there are two reactions going up. So let's just look at the applied force for the moment. So I'm just grabbing this one, copying it to the side. And we know this represents 5,000 pounds, right? So same thing, so same size. And this happens to be between the zone A and zone B. And somehow we want to be able to tell that from the force diagram. So one way to tell, always you're going to go from left to right, but we're going to label the start point of the arrow with A, end point of the arrow with B. So in a way you can tell this is an arrow AB. So at the force diagram you read the start point and end point, so this is arrow AB. But also in the form diagram you can tell this is AB because it's between A and B. So either way you go, this is called AB. It's between AB, this is starting from A, ending at B. So that's the applied force. But we also need to map the reactions, and because these are all vertical, we can connect them. And of course, because the whole thing is in equilibrium, this truss is not sinking into a ground, right? It's static, it's not moving. So it's being supported by these two reactions, and so you know that the total of these two reactions must be equal to a applied force. So first reaction on right side, right? So if I take this reaction, right, it's between the zone B and zone C. So if I follow this rule, right, this one was AB on this side, and it started from point A, ended at point B. Now we are looking at this force, which is between BC. We kind of always gonna go clockwise motion. So this is called BC. So in the force diagram, it must start from point B, which is here, and end at point C. So now we know the end point of that upward arrow is C. And I guess notice the fact that I'm, just to differentiate this and this, I'm using capital letters on the right side and lowercase on the left side. So we're gonna look at the next one, which is that reaction on the left. And if you look at these zones, it's between C and A. And name of that force, following this clockwise convention, this has to be called CA. And same thing on the force diagram. So this guy, which I'm gonna copy, is gonna be called CA. And following the rule for the force diagram, it's got to start from point C and end at point A. And it actually lands at point A because these two are half and half of the downward arrow. So that's the first step for the force diagram. Any questions so far? We good? Okay. So now you can read all of these texts later. So let me just, yeah. So now what we're going to do is that so far we've only looked at these zones that's outside of the truss. So now we are going to go in. Also, we are going to look at every point, corner point of this truss. So we're going to start from point R, we're going to go to point Q, we're going to go to point S. So kind of following that zoning rule, if I take the point R, if I zoom into point R, again, the entire, let's assume the entire world is this round thing, right? And it's divided by, now it's divided by these truss cause, the members of the truss and the force that's present in there. The reason being that if you look at this point, there's got, I mean, we don't know how much or which direction yet, but there's got to be, I mean, if you're pushing this point in this truss, we know from last class that each member of the truss only has axial force, right? It's either being pushed or being pulled. So this member must be experiencing whether a straight compression or tension along this direction. I mean, it's actually pretty easy to guess that it's in compression because it's like being pressed down. So there's got to be a force in this direction, whether it's going this way or that way, right? And also there's got to be a force in here. So even though we don't know how large or which way, we know for sure that there are some forces in these two. So the force divides the world. So if that round thing is the entire world, from, you know, center is R, between this force and between that force has to be seen as one zone, right? And
repeat that one more time.
yeah, so from where?
The zones.
Yeah, so, you know, it's kind of following the same rule, the forces divide the world into different zones, right? So there's got to be some force here, there's got to be some force here, there's got to be some force here. And now we're focusing on point R. So we have this round infinite world whose center is R, right? I'm just gonna, I'm drawing it very small. But now because we have this 1, 2, 3 forces, that's gonna divide this pie into 3 pieces, right? So we have this first piece, second piece, and third piece. Now, all right. So looking at that, we were able to call that force by referring to different zones, right? So this was actually, I color coded with this. So C is still here, right? Like this guy is still C. That's still A, consistent with the first labeling that I had. And this is these two, that's inside the panel, so we labeled that as 1, right? So looking at this point R going clockwise, there's the zone A, and then there's zone 1, and then there's zone C, and now you're back to zone A. Keep going around and around. Makes sense, right? So this force on the force diagram, we called it as CA. Let me go back to 2 views, actually. So that reaction, because it was between C and A, going clockwise, right, starting from C to ending at A, this reaction on the force diagram was called CA, which is this guy starting from C to A, right? Make sense? Right? So following that same logic, this force which is in this diagonal direction, that has to be called, anyone wants to guess the name that this force should be called on the force diagram if we were to draw one? A, where's B? B is way out here, right? So AB was actually, so let's see, this was going from C, going clockwise, right? So you go C, go across the force and end at A, so this vertical is called CA. Now we are looking at this one, you're going from A, going across this diagonal and ending at 1. Yes, so this diagonal force will be called A1. So because this diagonal arrow that we are going to draw here is called A1, right? The two letters, right? The beginning letter always represents the start point on the force diagram. So we know that there's got to be a line starting from point A, so this is going to be called A1, right? And point 1, we actually don't know where it is. Actually, it might be going the other way too, right? So, but we know that, so if you remember, the direction doesn't specify which direction specifies the angle, right? But this and that, for example, is the same direction, right? We call that as a sense. So let me look at the slide from structures 1. So for any vector, we have this thing called sense. So the direction is basically that particular angle. Sense is sort of where the arrow head is, so it could be this way or that way, right? So anyway, so at this point we know there is going to be a force A1 on this force diagram starting from A ending at point 1, but we don't know actually. One could be here or there. Right. Is it kind of hard to see the text? So one could be, at this point we don't have any information to lock down point 1, but we know for sure that it's going to be along this line, but we don't know where it is yet. Make sense? Alright, so we're just feeling what we can for now, right? Then so we kind of covered whatever we can for this force for now. Now we're going to look at this one, which is between 1 and C. So, and we're going to represent it in here. So what is this going to be called? Right, this was A1, this was CA, so this has to be going clockwise.
1C.
1C, yes. So there's going to be a force called 1C on this diagram. It's going to start at point 1, unfortunately which we don't know. It's going to end at point C. And fortunately we know where the C is, so we know where it's going to end. So this 1C thing is going to end at C. And it's going to start at 1. We didn't know where 1 is, but we knew it was going to be along this line. And now we also know 1 has to be on this horizontal line, right, which is parallel to this one. So now the only choice for point 1 is the intersection of these 2 lines, right? So that's basically where point 1 ends up being on this diagram. And now I can erase bunch of 1 question mark. So we can lock down this point 1, and also, so it's A1, right? And 1C was what we were trying to specify. So now, interesting thing is that, not to jump ahead too much, but so now we have analyzed point R. We got all the information that we could from point R, right? But we still have 2 more points, so we're gonna go to the point Q and point S. Yes.
Force diagram is just for that point R.
For now, yes. But we can now dictate that what forces are acting on point R, right? So we have this reaction, which was CA. If I want to determine what this force is, I need to grab A1, right? So it's basically this one, starting from point A, ending at point 1. So that's actually how much force is acting towards point R. So there's a force, and again, because we're drawing everything proportionally, the length of that vector matters, right? So this is 55. I don't like the fraction, so I don't like the feet, so I'm gonna do a decimal inch. So this line is like 55 inches, and if you remember our force scale, we were using this force scale where 15 inches was 5,000 pound, 1 inch was 100 pounds. So, and yeah, sure, right? So this was 50. Sorry. That applied force was 5,000 pound force, which is here and here, right? And now we have this diagonal force pushing the point R, that is 55 inches, so it's like 5,590 pounds. That makes sense? So we can actually determine the magnitude of this force by getting the length and applying the force scale, which we'll get to later. And we also know the direction of this force, it's pushing point R. So if you look at a point, right, if we are analyzing about a point, if the arrowhead is pointing to that point, that means you're being pushed, right? So then this member, the diagonal member, must be in compression, and also this reaction at point R is pushing the point R, so you're being pushed up, which makes sense. And so another thing we can determine is this guy, which is between 1C. So the force here is gotta be force 1C, which I can grab from here, starting at point 1, ending at point C. That's the force that's acting at point R along this truss cord. So now, because the arrow is going away from the point, I mean, it's pretty obvious, right? This point R is being pushed or pulled by this force. Pulled, yeah. This was being pushed, and this was being, R was being pulled by this one. So already, because it's symmetrical, we know, I mean, if this is pulling on its end, it's got to be pulling the other end opposite way, right? Because if it's going this way and that way, this cord is flying through the air, right? So it's going this way and that way, right? So it's pulling. So the bottom chord is in tension and top chord is in compression. So that much we already know actually, and which is, I mean, you gotta kind of have, I mean, I think I kept doing this last semester, but if I started doing the split, you know, my legs are obviously in compression, but at some point, like if I'm on the roller or something, I'm just gonna keep splitting, and I have to be like, if I need to remain static, then something's gonna be pulling my legs in, right? So that's kind of the easiest sort of intuitive analogy that you can think of. So it's very natural to think that these two are compression and the bottom one is in tension. Anyway, because we're trying to learn the process, I'm just gonna go step by step. So we're done with point R. So now we are gonna look at point Q. Right? And point Q, there's a force here, there's a force there, and there, right? And we've already named these regions, which I'm gonna bring in. So you have A to the left, B to the right, and you have 1 at the bottom, right? So if you zoom into point Q, you have force AB, which you already have, right, going from A to B, which, you know, that's the first thing that we drew. And we have this guy, which is B1, which we don't have yet. And then we have 1A. So
point Q a reaction still? Point Q is a reaction, right?
Point Q is a node on the truss, and this force that's acting on point Q is actually applied force, right? You're applying this force, and these two are the reactions, right? So in a way, if you make this like double, each of these reactions is going to be double too, right? But that's basically the load that it's supporting. Right, so we do have this already, which is AB, right? This diagonal, we don't have yet, but now the force in this chord will be called B1, right? Following the clockwise, right? It's going from B to, always follow this direction, right? So go from B to 1. So we already have point B and point 1 on the force diagram, so it's actually really easy to tell that force B1 must start from point B and end at point 1. And the arrowhead must be on this side because that's the end point. So you already know, if I copy this to that point Q, force in B1 is pushing towards point Q, which is in compression, which makes sense. And it's that length, and it's actually, you can see, because the diagram is symmetrical, that's got to be the same length as that, so it's actually equal compression to the other leg. So that's good. That's simple, right? And so next one that we're going to look at is this chord, which is between 1A. So the force in this chord must be called, louder, 1A, right? So it's gonna start from point 1 and end at point A. So which is we already looked at A1 at the other corner, right? But now this is called 1A because following this order. So it's actually going to be the other way, right? It's gonna start from point 1, ends at point A. So that's the force that's at point Q in this chord. And it's gotta be going this way because if the arrow is pointing the other way, it means that it's in tension, right? So, but now, just by following these steps, we were able to show this force pushing the point Q and that force pushing the point R. So that's what the compression member does, right? It tries to push back to this compression, right? So that's why it's in compression by that much. You can determine the intensity or magnitude of that compression by measuring this line and applying this force scale. So let's just do this calc, which is 555.9017 times 100. So that's how much force there is in, so actually that's the result. So 5590 pound compression. So we already know this is in compression. So now we are done with point Q, I think, right? We got all the data that we can get from point Q. So now we're gonna go to point point S. So same thing, zone B is here. Zone 1 is on the inside, and zone C is right there, right? So did I already draw this? Right, so we already had this reaction, which is BC, which is this way, and this horizontal one, now it's going to be called, anyone? Come on guys, come on, I need some energy.
C1.
Yes, C1. So it has to, so for this code, the force should be starting from point C, ending at point 1. So it's the opposite of this, right? So that's how much force is in at point S. It's pulling away from point S, and if you get the length of that, it's 50 inches, and that's why that's 5,000 pounds. And then what's this diagonal one going to be called?
1B.
Yes, 1B. So 1B, it's gonna start from point 1, ends at point B. So you're gonna show that at point S, and you can see it's pushing on point S. So that's why. And that was like 5900, right? 5590. So that's why you have, so let me just show compression here, compression there, and tension at the bottom, right? So basically this completes the diagram. So that's the diagram, and you basically measure this force, measure this force, measure this force. The direction kind of varies depending on which point you are in, but the bottom chord is in tension by 5,000 pounds. The top two diagonals are in compression by 5590, 5590. That makes sense? So, I mean, I think the kind of important thing is that you apply this force, and the force that's in this diagonal member is actually greater than, I mean, you would think, right? So the reaction is 2500, but now you have this 5,000, and you have this 5590 and 5590. You need these two forces that pushing towards point Q to basically achieve equilibrium with this diagonal, with this vertical force. Just to kind of reinforce that understanding, let's ignore the truss and let's just look at this point and these three forces, and they must be balancing each other, right? I mean, the easiest way to add up the forces by vectors is to always connect the tip to tail. So let's argue that this is a start point, and you add this vector to this one. You connect the tail to the head, right? So you connect three vectors. It's going to start from here, ends at the same point, meaning that the sum of these three forces are 0. So that's one way to look at it. Another way to look at it, which is, it might seem slightly puzzling that you need that much force to support just 5,000. But if you look at the component of these forces, right, both of these can be broken down. That was the wrong one. Both of these can be broken down to a vertical and horizontal component. So this force is equivalent to an addition of that vertical force and this horizontal force. This is also equivalent to addition of this vertical force and that horizontal force applied at the same point, right? So now, if you add, what matters is this vertical, right? If you add the vertical component of these two, that's actually completely equal to this applied force, right? So that's why you need that much force, because the vertical, what matters to equilibrate this vertical force is only the vertical component of that force. So from this though, now you should be able to guess, let's say, now we have a truss, right? Like this, and applied force here, right? And we needed that much force just to support that much vertical load because it's angled, right? So what I want to ask you now is, what if you change the angle of these trusses, right? Let's argue that one is shallower. Let's make it a lot shallower. Actually, let's make it like this. Let me make one really shallow. And let me make one really deep. And just by looking at it, so this was how much force. Let's copy point Q2. This was how much force that was necessary to balance out this vertical force at point Q. So if the truss got shallower and deeper, the force that's in this member, let's say option, let's just call it deep option and shallow option. In the shallow option, the force is in this diagonal member. Do you think it's going to increase or decrease from 5590? Increase, right? And what if it got deeper, that the force in here decrease, right? That's because there is, compared to the original one, there are a lot more vertical component in this force, in this angle, compared to that one. In this one, there are a lot less vertical component in this force. So meaning that, yeah, for sure, your truss, if you have more depths in truss, you have, generally speaking, you have less force in individual member. And if you have less force in individual members, those members can be thinner, right? So in terms of use of material, if the truss is deeper, you are more efficient, right? Because you can use less material. However, if you go too deep, then you're gonna, like, let's imagine, I mean, that's already pretty efficient, but let's imagine if I made that 3 times as deep, we can do away with a lot thinner material. But it's gonna stop making sense, right? If your truss is like 10 feet deep, it's gonna get in the way for, like, from architectural standpoint. So that's kind of always the balance. But just to kind of demonstrate the point, you know, this angle, right, it has certain amount of vertical and horizontal. So I can actually already guess how much I need, because I'm gonna need, it's gonna be split into 2 because it's symmetrical. So the vertical component of the left side only needs to take care of half of this force. So if I scale it to half, right, I'm gonna know already how much force is in. So it's gotta be, that's gotta be how much force that's in this member, which is compared to the original truss, right? That's a lot shorter, so this is more efficient. And if you use this one, then I'm gonna need, so just to take care of that much force, oops, so basically I need this much force to support this, because the vertical component of this force is only that much, which is half of this guy. So you can see just by looking at it how much more force is required in this member to support that. So the shallower you go, you become less and less efficient in terms of the efficiency for the truss. So that's, any questions? Does it make sense? This has to become almost second nature, because imagine that took a while to explain it, and it's basically the same thing here. It just takes a lot more process, and your diagram is more complex. So I really wanted to nail this so that we can quickly go through this next week. I mean, because right now we only have 15 minutes left, and I don't want to try to explain this one. So I will. So what I'm gonna do is, did I post? So I'm gonna post a homework. Did I do that? Okay. So, alright, so I'm gonna post. So this is what we did, and you have all of these explanation. So now I'm going to, okay, it's obvious, but I thought I exported it. Where did it go? Jeez. Okay, is that this one? Yeah, that's the homework. Okay, so I'm gonna give you this. homework file. So one's deeper, one's shallower, and this one's a little trickier. And it's probably not enough time. So why don't you... I have to set up the form for you to be able to submit the homework. So I'm just gonna post this file here for now, under the announcement. But I'm gonna create a separate link for submitting the homework. So look forward to that. So let's see.
We're going to do the same thing as last semester.
Hmm?
We're going to do the same thing as last semester, make the PDFs. And,
No. So what I'm trying to do. Okay, so this is probably something I should. Well, you guys did the. So let me post this here for now. But you guys, most of you guys did the dummy homework, right? So how that's gonna work is basically that's why it takes me some time to prepare, because anyway, so how that's gonna work is there's going to be a homework link, right? I'm gonna have week 2 assignment 1 or whatever, and then I'm gonna have a link to Google Forms, so you're gonna go to that link, and I'm gonna have a link to download the file, which actually I already uploaded to here, same file. And then I'm going to have Q1, Q2, Q3, which should correspond to, right, so this one's Q1, this is Q2, this is Q3, and I'll probably ask you in this form how much force is in QR, right? And then you're supposed to enter the number when, and sometimes it might be multiple choice, but you're gonna look at the problem in Rhino file and you're gonna enter your answer, and you can submit it multiple times, because it's not about grading you per this assignment. It's for you to get the feedback whether you got it right or wrong, and then yeah, and I need to enter my email, but it's gonna tell you, right, this is a different question, but once you submit it, it's gonna tell you which one's wrong, and yeah. And yeah, and I want you to post questions once when that doesn't make sense, so that I know which problem to cover